Hi, welcome back to Pre-Calc 40S. This is the second part of 3.1, R12. We're going to look at characteristics of polynomials. In this video right here, actually what you're seeing in front of you is page 109 of your textbook. I'm also going to recommend page 113 of your textbook as well. It's got a very nice summary of what we're looking at. We're going to look at the characteristics of polynomial functions. And first here what you see is right here, if you notice, this is a degree of 0. So when you have a constant function, your line goes straight across. And if you notice just right here, it's got the domain and the range listed, number of x-intercepts. Well, in this case, there are 0. It doesn't cross the x-axis at all. And the end behavior is extending horizontally. This one here is a degree of 1. It's a linear function. So if you notice, your end behavior, it goes diagonally across like this. It slopes up. It's a positive linear function. And your end behavior, the line extends down into quadrant 3 and up into quadrant 1. This is your degree of 2, so it's exactly the same as a quadratic or a parabola. And in this one here, the end behavior, the curve extends up into quadrant 2 and up into quadrant 1. And there are 2 x-intercepts for this. If we continue on and look at a degree 3 polynomial right here, this one, it crosses the x-axis 1, 2, 3 times, and the end behavior, the curve extends down into quadrant 3 and up into quadrant 1. And looking at this one here, this is a function that has a 4th degree polynomial. We've got 1, 2, 3, 4 x-intercepts. And the end behavior, the curve extends up into quadrant 2 and also into quadrant 1, so right here and here. And for the 5th degree polynomial right over here, you've got 5 x-intercepts, and the end behavior, the curve extends down into quadrant 3 and up into quadrant 1. Now, what I want you to notice, first thing is I want you to notice what all the similarities are between the squares and the, not the squares, but among all of the polynomials that are of even degree and the ones that are of odd degree. Sorry, my page jumped on me. So if we look at the ones that are odd, notice how the end behaviors, the opposite ends of the arrows, they're going in opposite directions, and the even ones, they are going in the same direction, so right here. This is an odd degree. They're going in opposite directions, and the even is going in the same direction, and this odd is going in the opposite direction. Okay, now what would happen if these had a negative leading coefficient? Well, let me take you here to this Desmos. It's an online calculator. If we were to look at x squared and then we were to compare it with negative x squared, now what does the end behavior do? Well, basically it reflects over the x-axis, right? So your the ends of the graph go into quadrant 3 and 4. So let's look at the x. This is just another example of a parabola. So the positive version and the negative version. And if we look at a Cortex power to the power of 4, we have up in quadrants 1 and 2, and the negative version is in quadrants 3 and 4. So we can just look at a different version of a, here I'll just show you that. Okay, so here this is a negative Cortex, so a negative function that has a degree of 4. The leading coefficient is negative, that's what I mean. And the end behavior is going down in quadrant 3 and in 4. And then for the positive one, it's in the positive direction, so it goes up in quadrant 2 and quadrant 1. All right. Now, if we wanted to have a look at the odd powers, so let's actually just look at this. I'll just, okay, so now let's look at odd powered polynomials. So this is y equals x right here. This is a straight line. Your end behavior, it's in the opposite ends, quadrant 1 and 3. If we compare it to negative x, if you notice here, it's going the opposite direction. Okay, so here this kind of looks like it has a negative slope, which it does. So keep that in mind. Now, so straight line, linear, positive slope, opposite ends in quadrants 1 and 3. And this one here, negative slope, opposite ends in quadrant 2 and 4. So if you just want to have a look at the cubic, this is what a standard cubic looks like, and this is what the negative cubic looks like. So just kind of take the positive one away, you could see the negative only. And so the end behavior is similar for all of the odd powered ones, and there's a pattern with whether the leading coefficient is positive or negative. So in the next page we're going to have a look at that and summarize all of this. So the next question, okay, so now using what we just looked at and summarized, I want you to try to match the following polynomials with the corresponding graph. And a couple of ideas is to keep in mind the leading coefficient, whether it's positive or negative, and also a good hint is to use the y-intercept to match it up with the graphs that are given. Okay, so take a second and see how you do. All right, so here's the reveal. The answers for 1 is B, and we match it up with B because of the y-intercept, and also you've got an odd degree polynomial which is positive, and this is what the end behavior looks like. First parts for C, graph C, we chose number 2. Number 2 works because you've got a 4th degree polynomial. It's negative, so the end behavior, both arms point down, and the y-intercept is at -6. For 3, that was graph D, and we have a leading coefficient of, it's a -2, and a power of 5. So it's a negative leading coefficient, so it's going to be, the end behavior is in kind of a negative direction, and it's of this type, or we could say it's x to the power of 5 type. So you've got kind of like 1, 2, 3, 4 bumps going on in there. And number 4 matched up with A, you've got your y-intercept of 16, and it's a positive leading coefficient, and it's the x to the 4th type. So both end behavior points in the positive direction. Okay, now this next question here looks at applications of a polynomial function. This first question, it says a toaster oven is built in the shape of a rectangular prism. Its volume V in cubic inches is related to the height h in inches of the oven door by the function V of h equals h cubed plus 10h squared plus 31h plus 30. Now, what is the volume in cubic inches of the toaster oven if the door height is 8 inches? So we're going to take 8 as our height and substitute into this equation here and solve. All right? So this is what the work looks like. And our answer is 1,430 inches cubed. So the volume is 1,430 inches cubed if the door height is 8 inches. Okay, simple substitution here. Okay, this next question says a bank vault is in the shape of a rectangular prism. Its volume V is related to the width W in meters of the vault doorway by the function. So this is our function here that's given. And then it says, what is the volume in cubic meters of the vault if the door is 1 meter wide? So we're going to take 1, so W equals 1, and we're going to substitute it into here. So why don't you substitute it into there? And you end up getting 140. So there's the work for the substitution. Sorry, having paper issues. All right, now if we plug in our 1 here in place of our W, we get the volume of the vault is 140 meters cubed. Okay, now this next question is a little silly. It says, what is the least of the volume of the vault? What is the least volume of the vault? Can't even read it properly. When the door is 0 meters. Okay, so that's kind of silly, right? But I guess it's just looking at all the material it's making up this vault if it didn't have a door. So plug in 0, and we end up getting 72. So this is the y-intercept, and it's also the constant term of the polynomial. So here's your answer. If the door was 0 meters wide, the volume of the vault would be 72 meters cubed. Okay, well, thanks for coming out. Hope that was helpful, and we'll see you again soon.